Welcome back. This is Mr. Hassan's Maths channel. I'm now going to answer question number 4 from the May-June 2022 um, International A-Level Cambridge 9709 paper 4 variant 3 from the mechanics. This is the mechanics paper M1. And here we have a diagram showing a block of mass 10 kilogram suspended below a horizontal ceiling by two strings AC and BC of length 0.8 and 0.6 meters respectively, attached to fixed points on the ceiling. Angle ACB is 90 degrees. There is a horizontal force of magnitude F newtons acting on the block. The block is in equilibrium. In the case where F equals 20, find the tensions in each of the strings. Okay, so here we're going to have two separate strings. We've got string we'll call this TA because it's going towards A, and we've got the tension in the string B, which I'll call TB. Right? So that's the tension. Those are forces acting on the block from the string. You've got this force 20 newtons. They say F is 20, so that's 20 newtons there. You also have the weight of the block acting vertically downwards, which is going to be 10 G newtons. 10 G newtons. So those are all the forces acting on the block. Okay, so we know the value of these two. These two are unknown. Okay, so what would make life easier for us here would be to resolve in the direction of these two tensions because they are perpendicular to each other. Because they are perpendicular to each other, TA and TB do not interfere with each other in terms of if I try to resolve TB in the direction of TA, its resultant force would be zero. Its result force would be zero. TA in the direction of TB, if we try to resolve it in that direction, it'll be zero. So if I resolve in the direction of TA and TB, that will cut out the need to have simultaneous equations. So I need to sort out my angles here, though. All right. Like I know that this angle, let's call it angle theta. I know that in this right angle triangle here, the tangent of theta would be opposite over adjacent. It would be 0.6 over 0.8. Now, if you notice that 6, that will give you 6 over 8, which is 3/4. So the tangent of theta will be 3 over 4. Okay? Which will make, if that was 0.6 and 0.8, that makes this basically going to be 1. Okay? If you think about it, because that would be 6, 8, 10 triangle. All right, so 0.6, 0.8, 1.0 triangle. So in any case, once we work out tan theta is 3 over 4, we can work out what sine and cosine theta are going to be. All right, from this, because you have a 3, 4, 5 triangle. That's theta. Tan of theta is opposite over adjacent. That means the hypotenuse must be 5 because of Pythagoras' theorem. That means the sine of theta must be opposite over hypotenuse. So the sine of theta must be 3/5. And the cosine of theta must be 4/5. So it's always best to be able to write the angles in terms of exact values. Now we got to try to translate those angles into the diagram down here. So like a good way to do it is to make it thinner without the arrow. Make it thinner without the arrow. Okay, so I'm going to draw a line like this. I'm going to draw a line like this. Okay, and I'm going to try and figure out what some of these angles are. Well, this angle is theta. Okay, and you can say that this angle is also going to be theta. Okay, because if this is theta, all right, and if I continue, let me continue this line as well so we can be sure. If I continue this line over here, okay, and this line over here, it will become clear. All right, so if this is theta, okay, then this is 90 degrees. Okay, this is 90 minus theta. So that's going to be, if this is theta, then this will be theta, right? This will also be theta. Okay, so I'll call this theta. Okay, because I want to resolve this force in this direction. Okay, and in this direction. Yeah, so this is theta as well. That makes life easier. So this is theta and that is also theta, right? They're vertically opposite angles. That makes life easy for me. I have an angle with this force, which I can use to So I need it with this force. I've got it with that force. I need it with this force, actually. So this angle, sorry, will be theta. I need to have the 10 Newtons in such a way that I can resolve it in this direction, okay? And also in that direction. So this is going to be theta, because here, this is theta, this is 90 minus theta, this is 90 degrees, so that's also theta. Okay, so just bear with me there. So I don't actually need to mark this angle here. In fact, I marked it in the beginning to be able to, just to show that this is the same as theta. I can even say this is corresponding to this. All right, so this is theta. So this is 90 minus theta, and this is 90 minus that. That must be theta as well. Okay, so whichever way you can figure out, I need to be able to resolve these two forces in the direction of TA and TB. So let me resolve the forces in the direction of TB first. Okay, so if we resolve the forces in the direction of TB, okay, then you're going to have TB, and this is going to be acting, if I resolve this force in that direction, okay, so I'm going to resolve this force in that direction. Let's make it different color. So I've got this force here, F. I'm going to resolve it in the direction of TB. Okay, so if you see I'm our theta, we're going away from theta. So this, in this direction, is going to be, you can say F, this is going to be 20. We know that's 20, so that's 20 times away from theta, sine theta. So this is TB plus 20 sine theta, and that's equal to this force resolved going into the angle, this direction, in the direction in parallel to TB. So it's going to go in the opposite direction to TB, parallel to it, but it's going to be 10g going into the angle, so it's 10g cosine theta. Okay, so that's going to be 10g cosine theta in this direction. 10g cosine theta. So that's equal to 10g cosine theta because it's in equilibrium. All right, so now that's going in the direction of TB. Now we're going to resolve in the direction of TA. Okay, so we have in the direction of TA, you have TA. Both of these forces are going to act in the opposite direction, so you're going to have equals. And then again, we're going to resolve this force, but in this direction this time. So again, this time we're going into the angle. Going into the angle, so we're going to use cosine. So this is going to be F cosine theta. This is F cosine theta, and F, as we know, is 20. So I don't need to put F, I can put 20 cosine theta, that's fine. That's 20 cosine theta. And we want to also resolve this force now in this direction. Okay, let me just put it slightly, make a gap between them so that they don't, whoops. I didn't mean to do that. Anyway, let me just fix this in place so it doesn't move again. Okay, so I want to take this force and I want to resolve it in this other direction. So this 10g newtons resolved in this direction is going to be 10g, and you can see here we're moving away from that angle theta this time. So 10g times sine theta. So you have TA that way, and this side you have 20 cosine theta. 20 cosine theta plus 10g sine theta. All right, so now we can work out what TB and TA are straight away. So TB is equal to 10g cosine theta. So that's 10 times cosine theta, which we said is 4/5. Okay, and it's going to be minus 20 times sine theta, and sine theta is 3/5. So we're going to find TB right away. So TB is going to be equal to, this cancels with this, gives you 2. You're going to have 20 times 4, which is 80, minus, that cancels with that, leaving you with 4. So 80 minus 12, that gives you 68 newtons. So we have TB equals 68 newtons. And if we look at the second equation, we have TA equals 20 times cosine theta, which is 4/5, plus 10 times sine theta, which is 3/5. Okay, so we end up with 5, and that cancels, leaving you with 4. So you have, that's going to be 4 times 4, 16, plus 5 and 10 leaves you with 2. That's 20 times 3, which is 60. Okay, so you end up with 76 newtons. That's TA. So we end up with TA is 76 newtons, and TB is 68 newtons. And here we have our answers. Now, that makes life way, way, way easier than resolving horizontally and vertically, because we don't have to use simultaneous equations here. Okay, and you've got simultaneous equations, you will have sine thetas and cosine thetas, and they'll be different. And it's going to be a bit of a hassle. So it's much, much easier to do it in this way. But it only works if the lines, if these forces are perpendicular to each other, because if I try to resolve TA in the direction of TB, it becomes zero. So I only have TAs and TBs in each equation. You won't have both in the two equations. Whereas if I resolve horizontally and vertically, I'll have TA something here and TB something there, and in both equations I'll have TAs and TBs, and I'll have to use simultaneous equations. Okay, so that's part A done, and now we're going to move on to part B. So it says, find the greatest value of F for which the block remains in equilibrium in the positions shown. Okay, let me just go back to here, and let me just take this, and I think I have to unlock it now. I should have prepared this earlier. And I'm just going to copy this and move it across. Okay, so it says, find the greatest value of F for which the block remains in equilibrium in the position shown. So what does that mean? I mean, normally it says find the greatest value of a force. It's like, okay, it's on the point of coming out of equilibrium, on the point of sliding, something like that, where, you got friction involved and you have F max. Well, there's no friction involved. This is just hanging in the air. What do they mean by the greatest value of F? Now, I'm sure some people would be stumped by that. But what you should think about here is just use a bit of common sense. Now, if you were to pull this with increasing force, okay, eventually what's going to happen is it will move, it will move. Okay, when it moves, what will happen to this string? When it moves this way, okay, what's going to happen to this string? Well, this string is going to become taut. Sorry, this string is going to become loose. This string, so just before this string just before it moves, this string is going to be loose. So it's like you're trying to find the limit such that the tension in this B is going to be zero. Okay, so you want to find the value of F such that the tension in this becomes zero. Okay, the tension in this becomes zero. That's what we're trying to find. Okay, so when the tension in string B becomes zero, okay, at that point, okay, that will be the maximum value of F for which it remains in equilibrium. So it hasn't moved yet. This has just become zero. So we need to have the value of F, okay, that makes, okay, F, the tension in string B equals zero. All right. So if the tension in string B equals zero, then we can simply just resolve the forces horizontally. Okay. So I can take the tension in A and I can resolve it in this direction. So the tension in A, I can resolve it in this direction. And we have to go through the angle theta. This is the angle theta here. Okay. So we have to go into the angle. So this will be T A times cosine theta, okay, and this is going to be F, and the weight is going to be acting straight down, as we know. So you're going to have the weight acting straight down, which is 10G. So we can work out what TA has to be for when that happens by using or resolving this force. Okay, resolving this force in this direction, okay, vertically. So that's going to be TA times, going away from the angle, sine theta. So if we resolve the forces vertically, we have TA sine theta. Now TB is zero, so we don't have to worry about that at all. So that's equal to 10G. These are perpendicular to that. So in this case, resolving horizontally and vertically works out, of course, better. Now we know that sine theta was 3/5 from the last question, last part. So we have TA times sine times 3/5. Okay, so 3/5 TA equals 100. So we can work out what TA is going to be. That's going to be 100 times 5. That's 500 over 3 newtons. Okay. And then we can work out what the other angle is going to be. So not the other angle. We can work out then the horizontal components. So horizontally, we have F is equal to TA cosine theta. So we know what TA is now. So F is equal to TA, which is 500 over 3 times, and we know that the cosine of theta is going to be 4/5. Okay, just to make sure of that. Yep. So the cosine of theta is 4/5. So it's 500 over 3 times 4 over 5. 5 goes into 500 100 times. So we're left with 400 over 3 newtons. Okay, so F is equal to, we can leave it like that if we want to. Okay, we can say 400 divided by 3. That gives us 133. You can say 133 newtons is the maximum value of the force F, such that this will remain in equilibrium. It will stop being in equilibrium as soon as this becomes 0. Okay, and for it to be in equilibrium, therefore TA cosine theta and F have to be balanced out. If F becomes more than TA cosine theta, it will go out of equilibrium. Okay, but the maximum value of F would be such that there's no TB supporting it. It's just F on its own. TB has become 0. It's just become slack. Okay, just the tension has gone from TB. Or you can say the tension is just about to go. It's just about to become completely slack, but there's no force pulling in this direction with the F. So then the F will have to just match TA cosine theta, all right, with no help from TB. That will be the maximum value of F. I hope that was clear. It's a bit of a tricky one. You got to think a little bit about it, but it's that's what you need to do in mechanics. Have a bit of a thinking cap on. So anyway, that question is number 4. Other questions from this paper can be found in the playlist that will appear in this region over here. Other questions from the topic of statics, which this is from, can be found in the playlist over here. You can subscribe to my channel by clicking on this link. In fact, you can see other statics problems from the mechanics of Edexcel, which I have a lot of videos on. Just be aware that the value of G we use there is 9.8 and here it's 10. That's the only difference. And you can see lots of different examples of that there. And here you can subscribe to my channel by clicking on this link. Thank you for watching and see you soon.